Okay, the time has come to get a little excited with some sine and cosine graphs. So let's first talk about periodic functions. Sine, cosine, and tangent are periodic functions because they repeat on regular intervals. And those intervals are called cycles. Okay, so the length of a cycle is called its period. So for instance, the phases of a moon, the period of the moon is 28 days because that's how long it takes it to get through an entire cycle of all of its phases. This is an example of a periodic function. It's repeating exactly over and over. This is an example that's not a periodic function because you can see it's not doing the exact same thing over and over again. I could break this into one and then another, and then we can presume that another would be repeating. Okay? Now, here's a little bit of vocabulary. The period is the length of the space that it takes to complete a cycle. On the standard parent graph of the sine and cosine graphs, the period is 2 pi. One complete rotation around the circle is the same as one complete rotation through the graph of the trig function. The amplitude is the height, or how much vertical space it takes up. It's always going to be half the distance from the top to the bottom most points on the graph. It's always positive because it's the distance between them, okay? In the parent graph, the amplitude is always 1 because I'm going from positive 1 to negative 1. That's 2 spaces divided by 2 is 1. And then write down the way that a equation looks once it's had a whole bunch of things done to it. We're not going to spend time on this right now, but we will in class. It's very similar to the same way that equations of functions for quadratics or cubics or absolute values, all of them are handled the same way. Notice you've got your h and k are back again. This k affects vertical up and down shift. The h inside here affects horizontal shift, and just like always, it'll take you in the opposite direction that you expect. B, right here in front, affects the period. So the normal period is 2 pi, but if I have a number in front of here, it's either going to smush it so that it has its cycles more often, or it's going to stretch it out so that its cycles are less frequent. Okay? And the one on the front is the amplitude. This is the one that used to affect our vertical stretch. It still will. So this is going to make your waves go even higher or make them more compact. Okay? It affects your up and down stretching. So these same features of your functions are going to appear with trig functions. And so it's important that you have that sample equation in your notes. Now let's look at it. Okay, this is a sine, S-I-N-E, sine graph, okay? So what happens is I think about the unit circle and I think about the values because really graphs are just, I place ordered pairs. One thing that's a little bit different now is take a look at my x-axis. I'm not using numbers on my x-axis, I'm using pi. So 2 pi represents one complete cycle around my circle. Pi would represent half, and then these would represent the halfway point between each of those. So I have a value of 0, 0 to start my graph, and that's because when my angle equals 0, look at the value of y. Y is not going up at all, so y is also 0. So when my angle is 0, y is 0. When my angle is pi over 2, which is right up here, notice my y is its very tallest. It's at 1, so that's my peak. When I come back over here to pi, see I'm moving around, and I've got to pi, look, I'm not moving up or down with my y anymore, so my y equals 0, and that's 0. Now I keep moving around, and now look at my y. I hit my bottommost level of my y at 3 pi over 2, and here it is. And when I come back around to the end, 360, I'm back where I started, where y equals 0. Boom. Okay? So it's based upon the values of the ordered pairs that we have placed onto the unit circle. That's why it's so important that we can understand the unit circle in terms of radian measurements so that we can compare those to where we're placing them on the graph. Okay? The important thing to notice is look at the way the movement is, one complete cycle. Let me stop it right there. There we go. And that sine is going to start at 0, 0 unless it gets moved. And one complete cycle is top half, bottom half. Okay? So let's take a quick look at cosine. Cosine's different because cosine refers to where x is. So when my angle equals 0, x is all the way over here at 1. So it starts off at 1. When my angle is 0, x is at 1. And then it comes up here to pi over 2. And now my x, I have no side-to-side movement at all. So that equals 0. And now here I am at 0. When I come over here to pi, halfway around my circle, now my x is at its lowest maximum, -1. And here it is at -1. I come back around, and now when I come here to 3 pi over 2, I have no left or right movement. I'm on the axis, so my x equals 0 again, and here it is at 0. And finally, when I finish, I'm at my greatest value of x again at 1, and it comes back up. So notice how the graph of cosine is different from the graph of sine, because what's happening to the x's is different from what's happening to the y's. That's the reason. So it's always going to be like a little cup for cosine, okay? Unless it gets moved around by transformations. So this is one complete cycle starting from the highest down to the lowest in the middle and back up to the highest again for my standard cosine function. Now, how are you going to graph these things? Well, the steps to graph this, you're going to notice we're always going to be over here and have sort of a more stretched out coordinate plane when we graph these, because we have we're going to have our movement going from side to side much more than it's going up and down. So the first thing is to mark the key points. So every time I go to graph a sine or cosine function, I first start by putting in my 0, my pi over 2, pi, 3 pi over 2, and 2 pi. Those are my key features or my key points. That represents, if you think of the circle, that represents like my 4 corners or quadrants on that circle. So I put those down. And then I'm actually going to go find the value of the ordered pair at that. So it, depending on whether I'm using sine or cosine, will determine which number or which one of those ordered pairs I'm going to choose. But I go to find those, and I place dots where they are. So for instance, if this were sine, I'd place a dot here at 0, and then I'd place my dot, where am I? Boom, pi over 2, high point, pi, low point, 3 pi over 2, low point, and pi over 2, high point. So first I just place my dots. And then last I fill in the curve. Now this one I'm using the standard dots, but I also could use any of those angles that we have learned. Oops, that didn't work very well. I could use any of those angles that we've learned on the unit circle. Okay, so depending on the kind of application that you're doing, you may or may not be using these same exact ones. You might be using pi over 3 or 3 pi over 2, and that's fine. Or square root of 3 over 2. So this is the standard steps, though, as you're thinking about it. Always fill in those dots. Always place your radian measures here and fill in the dots, and then fill in the curve. So let me show you one that I did a little differently that needed something different. Okay, remember those ordered pairs on the unit circle, they create the graph. So what I did here was I was looking at my theta, okay, where my angle measure was, and instead I chose pi over 3, okay, which is a 60-degree angle, 5 pi over 6, which takes me around to the other side of my unit circle and is a 30-degree, 4 pi over 3 is another 60-degree, I'm going down to the third quadrant, and finally in the fourth quadrant I have 11 pi over 6. So all I did here was to try to show you that now I'm going to make those marks on here for what the values are. So how in the world do I find what I think the value of square root of 3 over 2 is? Well, you can place that in your calculator to get an approximate value. It would be about 1.7 divided by 2, so it would be about 0.8. So you'd find this and come along here and say, okay, that's there. All right? And you could work in using your calculator. Of course, we know what 0.5 is. So at 5 pi over 6, I should be at 0.5. Okay? And then coming down at 4 pi over 3, I think I'm at way down again. And then when I almost get to the end, I'm back to 0.5. Okay? Again, dots first, sketch in the curve second. Okay? This is a lot to digest. The important thing is to have this in your notes, and we will spend the next several days just working with transforming these graphs and putting them on the coordinate plane.